This video is about electrodes and conductivity. It corresponds to section 38.1 of the textbook. The notion of an electrode is a fairly simple one. It's a transducer that takes electron current in a wire into some other form of current. And that other form of current for bio applications is often an ionic current in a solution or in a biological system. We also get it, you get the same notion of an electrode if you have a vacuum tube. In a vacuum tube, it's an electron current in a vacuum. And you get the same notion of an electron in a semiconductor, where you may have electrons or holes as your charge carriers. So electrodes means a lot of different things in different applications. There are two special names that get used, and that's anode and cathode. And these terms are a little confusing. Chemists like to talk about them in terms of what sort of reduction or oxidation reaction is going on. And I find that difficult to memorize. What I can remember is that if we think about this in terms of electrons, cathodes are where electrons leave a wire. And the anode is where the electrons enter the wire. How does that easy for me to remember? Well, what I do is I remember the old television sets, which were cathode ray tubes, and the cathode rays were electrons. And so the rays that came from the cathode were the electrons leaving the wire that was the cathode and entering the vacuum. So cathodes are where the electrons leave the wire. And we get that in our semiconductor stuff by looking at diodes, where if you remember, the current flow goes in the direction of the arrow. So this is the cathode and this is the anode, because the electrons leave the wire and enter the diode on the cathode side. Okay, so just a little bit of nomenclature there for electrodes. We have this section is mainly going to be, though, about conductivity. And that's not something that's a property of an electrode, it's a property of a material. Let's think about having two electrodes. Let's say they're circular electrodes at either end of a cylinder. Okay, so if we measure the resistance of this cylinder, we'll get a particular value. But if we make the cylinder longer, so let's call S the separation between the two electrodes there, if we make that longer, the resistance will go up proportional to the length, because think of it as being more resistors in series. And similarly, if we look at the area of this on the end here, if we put two of these in parallel, we would have a lower resistance. And as we put more and more in parallel, as we increase that area, we would decrease the resistance. So the resistance is going to be some constant times the length divided by the area. And this resistance will change depending on exactly what the geometry here is, but this property here, which I've written here as a rho, is resistivity, and it is a property of the material that we're making this cylinder out of. So if this is a salt solution, the resistivity of the salt solution can be determined by looking at the resistance, measuring the resistance, and then correcting for the geometry. Now this particular geometry that we've got here with two flat plates at the end of a constant cross-section cylinder, or actually any prism. You can do rectangles or triangles as long as it's a constant cross-section. That geometry is not a very common one for actually making measurements, because it's a little bit difficult to arrange when you've got to do flow and things like that. So what we usually have is a different geometry for the electrodes, but fixed. So we fix the geometry, we make the electrodes rigid, put them in the solution, and then measure the resistance between the pair of electrodes. We have to correct then for the geometry of the arrangement of the electrodes that we have. And it's not just going to be separation over area, because it's not this simple cylindrical object. In particular, the ones that we're going to be using in our lab is a pair of skinny cylinders some distance apart. And it is possible to calculate what analytically what that geometric factor should be. And there's actually a formula for it in the book. It's not an easy calculation to do. It involves doing Schwarzschild formulas and stuff like that that are way beyond the scope of this class. And what they're doing is they're correcting for the sort of the field lines you get, as here everything was straight lines from one end to the other, but here they're, if you look at it sort of in cross section, you've got electric field lines that run like that. And it's possible to calculate what that should be. But if you've got slight variations on the geometry, like this is based sort of on a two-dimensional infinite cylinder. If you've got ends on the cylinders, then there's different things going on at the ends. The calculations just get really, really messy. And so what people usually do is, when they want to measure something, they take their electrode configuration, whatever it is in the real world, and use a known resistivity solution, a particular concentration at a particular temperature, so they know exactly what it is theoretically, use that as a standard, measure its resistance, and then they can measure resistance of an unknown and have a calibrated geometric factor based on actual measurements of a known solution. So it's very rare actually that people use these complicated calculations to figure out the geometric factor. They nearly always do it just by empirical measurement. Okay, so what are we going to be measuring? Well, what we're going to be measuring is salinity of a solution, or we'll be measuring that indirectly. More directly, what we'll be measuring is the conductivity of a solution. And let's take a look at what that means. Here I've plotted some reported measurements from the literature. Again, these numbers are in the book, along with citations, of conductivity versus concentration of sodium chloride in water. And what you would be measuring in the lab, if we've got a standard lab setup, is some known concentrations of sodium chloride in distilled water. And what you'll see here is that the conductivity is measured in microsiemens per centimeter. What's conductivity? Conductivity is just the inverse of resistivity. Remember that resistivity, let's go back to, resistivity was this number rho. And if you take a look at it, we've got ohms on this side and centimeters over centimeters squared here. So the units for resistivity is in ohm centimeters. It could be another unit, could be ohm meters, but centimeters is most commonly used. And then for conductivity, which is just 1 over rho, the units will be Siemens, which is 1 over ohms per centimeter. Okay, so why do we use resistivity or conductivity? I mean, resistivity seems like it's a natural thing here because we're measuring resistance. Conductivity gets used because it is basically proportional to the number of ions in the solution. So going back to our plot here, we've got a straight line here that's basically just that the conductivity is proportional to the concentration. And that works really well for very low concentrations. When the concentrations get higher, we start seeing deviation from that. It's also dependent on the temperature, and we have a higher conductivity at a higher temperature. And so when one's measuring the salinity of something, generally you measure not just the conductivity but also the temperature, so that you can correct with some standard formulas for the effective temperature as well as in order to compute the concentration. In biological systems, it's very common to measure, for instance, environmental variables like what's the concentration of the ions in tap water, in river water, in seawater, and measuring the conductivity is a very simple way to do that. People also measure the conductivity of blood serum. And it's one interesting thing there is that if you're measuring blood, the blood serum has a concentration of about 13 millisiemens per centimeter, or 13,000 microsiemens per centimeter. But whole blood, which has got the red blood cells in it, has only about half that concentration because the membranes of the red blood cells are non-conducting. The lipid bilayers, the lipid's not conducting. It doesn't let ions through it. And so the slurry that you have of whole blood, where you've got a lot of blood cells mixed in with the serum, reduces the conductivity of the serum. And that actually can be used for measuring the concentration of blood cells sort of very rapidly, just by measuring the conductivity of the whole blood. Let's see, what other things might you want to know? The conductivity of seawater, which I mentioned before, is quite high. Seawater is around 50 microsiemens per centimeter. So, and I just told you that blood serum was about 13,000 microsiemens per centimeter, with seawater being at 50,000 microsiemens per centimeter. You can see that seawater is more concentrated salt than blood is. Despite what some people say about us having the ocean inside us, we're diluted. Another place where concentrations are measured quite often for microbiology labs is how pure your ultra pure water is. Companies like Millipore, which makes water purifiers for labs, will claim something like 18.2 mega ohm centimeters. Now they switched to resistivity rather than conductivity because it's the numbers get very small if you're starting to look at microsiemens per centimeter. So they do the resistivity instead. That 18.2 mega ohm centimeters that Millipore claims, you don't really get that, because to get that you have to dissolve monatomic gases, argon or xenon or helium or something, in the water, because if you just expose it to air, water that pure would pick up carbon dioxide. The carbon dioxide would form carbonic acid, which would split into H plus and HCO3 minus ions and increase the conductivity. So the resistivity of really pure water in air is only about 13 megohm centimeters. So the ultra pure water really requires special handling if you want to really get that low a conductivity. Luckily for biology purposes, we're usually not that interested in the conductivity directly. We're just interested in how much contamination we have, usually interested in things like sodium and chloride ions. Usually H plus and HCO3 minus ions do not greatly affect the biological results. So exposing your ultra-pure water to air is, for molecular biology, usually not a major problem, unless you expose it to air in a way that you get dust or something in it, and then all bets are off. Once it's not sterile, it's no longer useful. Regular distilled water, if you just run stuff through, get stuff directly out of a still, and don't do the ultra purification, then you'll get something that's, say, 10 microsiemens per centimeter. So nowhere near the 0.055 microsiemens per centimeter of the ultra pure, but still a lot better than tap water, which may be 50 to 500 microsiemens per centimeter. So lots of different concentrations, and you can see that this entire range of concentrations of ions in water get used in biological labs. If you do stuff with David Bernick's lab, they do a lot of things with halophiles, where things are growing in 3 molar, 4 molar, even 5 molar salt, and that's all the way up at the point where it's saturated. You can't dissolve any more salt in the water. And things grow under those conditions. So this entire range of concentration is stuff that is biologically meaningful, from the ultra pure water at one end used for a lot of laboratory work, and the very high concentrations that you'll see for halophiles. What you're going to be doing in a subsequent lab is doing a bunch of measurements to measure different concentrations of salt water in order to determine how the electrodes behave, and we'll talk about that in a subsequent video.